Alrighty, so my objective is I can calculate and plot the total number of microstates and corresponding entropies for a two-object system with an unequal number of oscillators in each object and over 50 quanta of energy dispersed between them. So that's my little statement prompt. This is supplemental. Okay, here's my prompt that I wrote for myself. So we have a two-object system with one, actually it's not one oscillator. It's 3 oscillators in one box and 4 oscillators in another. So a two-object system with 3 oscillators in one box and 4 oscillators in another. What are the total number of microstates and corresponding entropies for their system? And there are 50 quanta of energies dispersed between them. And then I'm also going to plot the graphs of them as well. And just for reference, the calculating the microstates omega to arrange the q quanta among n one-dimensional oscillators, you use omega, you use this equation, this omega q plus n minus 1 factorial over q factorial times n minus 1 factorial. And then for, it looks like entropy, what do we use? We use the Boltzmann's constant times the natural log of omega tot. So that's what we use for equation-wise when I reference them in my graphs. So getting rid of the graphs real quick. So I started out by graphing my Q1 and Q2. As you can see, I graphed all of my 0 to 50, and then I graphed 50 to 0. So, getting every possible combination in there. And then, so for omega 1, you can come up here to the screen at the very top and see the little equation I used. I used factorial of A2, so that's Q1 plus 3, and 3 was held constant through when I scrolled this down because you just put a dollar money sign in front of it to hold it constant. Minus 1 divided by the factorial of A2, which is 0, or the Q1, the energy, times the factorial of n minus 1, which is just 3 minus 1. So then you just kind of take that little cell and you just drag it down, and then it just gives you the corresponding omegas for Q1. And then you do the same thing for omega 2. And here's my equation. See how it highlights 4, and then you go over here, and now it highlights 3. So I use 3 for this one and 4 for this one, unequal number of oscillators in each box, and you just kind of drag this down. So after you have omega 1 and omega 2, you can calculate omega tot. Omega tot is just omega 1 times omega 2, and that's the total number of microstates in for this particular system, having 0 quanta of energy in one box and 50 in another. So, and then to plot that number of microstates, let's see, here we go. So in order to plot that, what you can do is you have this graph, you can take omega total versus Q1, the number of energy for quanta 1 for one of the boxes, and then it kind of gives you this graph, and it kind of shows you the total number of microstates over 50 quanta of energy in between two objects. So that's what I did for that one. And then for the next one, I did entropy. So for entropy, take this graph over here. It's entropy, which is in joules per Kelvin over Q1 quanta of energy. And for this, I just took, I just took Q1, and I didn't include the 0 because it was creating this line from here down, which did not look pretty, so I didn't include 0. And then you just graph entropy joules per Kelvin. Now for the joules per Kelvin, for entropy, it's just equal to the Boltzmann's constant times 1.38 times 10 to the negative 23rd times natural log of omega. And for natural log of omega, I just took the omega tot cell and times it by the natural log. And then, yeah, so then you just take entropy and then graph entropy over Q1, and you kind of get this nice looking curve going on. So that is it.